Right, Assalamualaikum and a very good day to everyone. So today we will continue our next lesson, which is regarding on the bipolar junction transistor. Okay, regarding on the DC circuit analysis, right? And from our previous class, okay, we have covered some of the chapter. All right, so we have looked into the common emitter, what is common emitter, what is common base, common collector, and we have not discussed on the DC analysis on the Q point using the graphical and the mathematicals. All right, so today inshallah we will cover all this. All right, so okay, so from our previous class we have discussed on what is the BJT function of the BJT, right? It is used as an switch, okay, as a switch, and also as an amplifier. All right, so at what region it's work as an amplifier is at the active region, and what region that it gonna work as a switch, it is at the cutoff and saturation region. Okay, so cut off, the switch will be completely off, and at the saturation region the switch is completely on. All right, and for the DC analysis, all right, what you need to consider is there are two junctions that you need to consider, okay, which is the BE junction, which is the base and emitter junction. Okay, base and emitter junction, so this is the BE junction. And you also need to know the BC junction, which is the base and the collector junction. All right, so the BE junction, usually it is in a forward bias. All right, so what is the value of the voltage drop? So the voltage drop usually is 0.7 volts, or if it is mentioned a specific value, then you have to use that specific value. But if it is not mentioned, then we're going to use the normal voltage drop, which is 0.7. Okay, that is the typical value. And for the BC junction, usually it is in a reverse biased. All right, so how to analyze the DC analysis? Okay, if there is a capacitor, the rule is we need to assume all the capacitors are in open circuit. Okay, so meaning that this capacitor at this area, it will gonna be open circuit, so there gonna be no current will be discussed, or will be flowing on this area. So also for this C2 capacitor here, also we're going to be open circuit, so there will going to be no current flowing here. And at the C3 capacitor as well, there will going to be no current flowing here. So therefore your circuit here can be simplified to be as such. Okay, so at the beginning for the DC bias analysis, it's very easy. You don't have to consider all these capacitor. We will discuss in detail on these capacitors for the AC analysis later. Okay, and if you want to find, or if you want to analyze a DC analysis, okay, we always will relate with the operating region, which is known as the Q point. Okay, so what is Q point? Q point, you have know this Q point when we discuss about diode, right? So Q point is the operating region, meaning that on that particular region, okay, your amplifiers, okay, your transistor amplifiers is working. All right, okay, it is in an amplification process. Okay, so if it is not working, then it is not at the Q point. All right, so it is very important to find the value of operating region. Okay, and then okay, these are the types of biasing circuit that we will discuss. Okay, we will discuss on fixed bias. All right, okay, we have discussed this fixed bias in our previous class. Right, and then we will also today cover the emitter stabilized bias and voltage divider bias. All right, so there's also others bias, but we will not discuss this. Okay, so we only focus on these three: fixed bias, emitter stabilized, and voltage divider bias only. All right. Okay, next, so here are the rules, okay, important equations, all right, for the analysis, all right. So the VBE, okay, voltage at base and emitter. So where is the base and emitter, if you still remember? So here is our BJT, okay, here is your base, here is your emitter, and here is your collector, right? So voltage across here is known as VBE, okay, and voltage across here, okay, can be either 0.7 if it is a silicon, or if it is germanium, it is 0.3. Okay, usually it will mention what are the types of the transistors, so you don't have to worry. And then for this equation, you have found this equation on our first part of BJT. I have introduced to you this equation where beta is equals to collector current over base current. Okay, current at the collector, okay, IC, okay, divided with the current at the base, okay, which is IB. Alright, so you will get the value of beta. So beta is the factor, gain factor. Alright, and IE, where is IE? IE is the current at the emitter. So current at the emitter is equals to IE is equals to IC, current at the collector, plus with the current at the base. Alright, and then okay, so if you if you alter this equation and you replace inside here, because we know IC is equals to beta IB, so you will get this equation. Alright, okay, so this equation is coming from this equation, equation number 2. Okay, we replace or substitute inside equation number 3. Okay, so you will able to get this equation number 4. Alright, so equation number 5. Okay, so equation number 5 is a special equation, because if you still remember, on our first part of BJT, I did mention to you that alpha, which is alpha, is equals to IC over IE. Okay, and if you remember, okay, there's a slide in BJT part 1 that has been introduced to you in the previous class. Okay, you please refer to that slides again. Okay, we did mention that a good amplifier, okay, good amplifier, the value of alpha is equals to 0.9999, or it is almost to 1. Okay, so if this value of alpha is almost equals to 1, meaning that IC divided with IE is equals to 1, so therefore your IC is equals to IE. Alright, so that's why this equation can be performed. It is by assuming that your transistor is a good amplifier. Alright, okay, so in our first class, we have discussed, on our previous class last week, we have discussed on the fixed bias, which also known as a base bias. Okay, so this is the simplest type of the transistors, and however it is unstable because of why? Because the value of beta is changing based on the temperature and the collector current, meaning that it is solely depending on the value of the collector current. Okay, so how to know that it is a base bias or fixed bias? You can look at the base, it is connected to the collector, it only have one source. Okay, rather than, okay, on our common BJT circuit, we're gonna have VBB usually, another base, another voltage source at the base. Okay, and then alright, so VCC. Okay, so we're gonna have separate voltage source at the base and at the collector. So if you look at here, we only have one voltage source, which is known as VCC. Okay, and your base is directly connected to the VCC. All right, so it is very unstable. Please remember this, okay, because this might be asked. Okay, it is very unstable. Okay, because of why? Because the value of beta, okay, remember beta is equals to IC over IB. Okay, by right, you already should have all this formula at your fingertips. Okay, all right, so it's very depending on with the value of beta, which this value of beta can easily be changed with the different temperature and the collector current. Okay, so collector current is depending on the VCC as well. All right, so how to analyze this equation? All right, so I have explained to you right before. First of all, we need to remove the capacitor. Okay, so these are the rules. If there is a capacitor, you need to remove this capacitor, remove this capacitor, remove this capacitor. Okay, and what else? Okay, the DC supply we're gonna be only the VCC. Okay, so this VCC you can separate into two loops. Okay, there are two main loops that you need to consider, which is one is known as the BE loop. Where is your BE loop? Here is your BE loop. Okay, here is your BE loop. Okay, so this is known as BE loop. Okay, and another one, okay, another one, all right, another one is the CE loop. Okay, so where is your CE loop? Here is your CE loop, from here to here, here and here. Okay, here to here, 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 here. So this is your CE loop. Okay, so you have to separate these two loops. Okay, all right, next. Yeah, so therefore your circuit will gonna be simplified as such once you remove all the capacitors, and we consider the two loops. Okay, one is the BE loop. Okay, here is your BE loop, and another one is your CE loop. Here is your CE loop. Okay, so here is the BE loop, here is the CE loop. Alright, okay, so next what you have to do, next you need to do the KVL on this, right? Okay, so the KVL for the first loop, yeah, for the BE loop, it will be, this is your voltage source, so it's gonna be VCC, okay, positive VCC, so your current will flow here, so this will be the positive, here gonna be negative, here we're gonna be positive, and here we're gonna be negative, right? Okay, so it's gonna be VCC, alright, is equals to, alright, VCC is equals, this voltage source is equals to RB, okay, IB, RB, alright, and then plus VBE. Okay, so voltage drop across this resistor plus this voltage, of course it must be equals to this VCC. And then if we want to find the value of IB, then you have to do the rearrange the equation, so you will get as such, and then you will get the value of IB. So once you get this value of IB, remember the main formula previously, okay, which is IC is equals to beta IB. So you already know the value of IB. Beta is already usually will be given to you, then you can calculate the value of IC. Alright, so once you know the value of IC, once you know the value of IC, collect the current, then we can proceed to the CE loop. Alright, so the CE loop, this is your loop. Okay, so VCE, remember this is the area of the VCE. So what is the KVL? We need to start with the KVL. So again, the VCC, this is the voltage source, is equals to the voltage drop across RC, so it's gonna be ICRC plus, so this is the directions of positive, negative, right, of the voltage area at the collector emitter junction. So plus VCE, so it's gonna be equals to the VCC. So IC is the one that you have calculated from the BE loop. Okay, from the BE loop, then you can find what is the value of VCE then. Alright, so once you know the value of VCE, remember voltage of VCE is equals to voltage at point C. Where is the voltage at point C? So here is the voltage at point C minus with the voltage at point E. So here is the voltage at point E. Okay, and usually your VE is connected to the ground, so it usually equals to 0 volts. So hence, because of that, your VCE now is equals to VC, and you can calculate the value of VBE as well, right? So VBE is based on the value of VBE, usually based on the types of the transistor, either it is 0.7 or 0.3, right? Okay, so VE same as previous, usually it is equals to zeros. Then in that case we can find the value of VB. All right, so VB is equals to VBE. All right, okay. And we also have discussed on this example. Most of you can get this answer. Sorry, because this is the answer is provided to you, all right? And we have done this exercise 1, right? So now I think I'm not sure, did I explain about the disadvantages of the fixed bias or not? But we will discuss this on this class, right? Okay, so the disadvantages of the fixed bias, remember, before we go to the disadvantages, what are the advantages of the fixed bias? The advantages is it is the simplest circuit. Okay, the circuit is very simple. Okay, the simplest circuit. Okay, however, what are the disadvantages? Okay, the disadvantages is the word is unstable. All right, remember it is unstable because of why? Because of the value of beta. Okay, it is too depending on the value of beta. Okay, which the value of beta can easily be changed by the temperature. Okay, or the value of the collector current. Okay, all right, and okay, so that is the first reason. And produce with change of the Q point. So once your beta change, okay, your Q point also, the Q point region, the operating point, okay, the operating point of the transistor also will change. Okay, the operating point of the transistor also will change. Okay, we have discussed that for a good transistor, the operating point must be at the center of the graph, right? So if your Q point is changed, if it is go nearer to the cutoff, then it gonna be have a clipping, right? The wave gonna be clipping. If it goes to the nearer to the saturation region, it also will produce a clipping. So in this case, your transistor is not to be a good amplifier. All right, the area that your transistor will gonna be a good amplifier is at the center of the graph. Okay, if you can draw the DC load line, it's gonna be at the middle of the DC load line. All right, so to improve, okay, so in order to overcome the disadvantage of the fixed bias, right? So there's another circuit is introduced to you guys, which is known as bias stability. Okay, which is known as bias stability. So what are the different? What did they add to this bias stability? They add an emitter resistor, which mean at the emitter junction just now for the fixed bias. Okay, for the fixed bias, if we can recall it again. Okay, so this is your transistor. Okay, so here is your, oops, okay, let's make it longer, then it's gonna go there right here. So this is your VCC, all right, and here is your RB, here is your RC. Okay, this is your base, this is your collector, this is your emitter. At the emitter, there, if you can look here, yeah, the emitter for a fixed bias, there is no transistor at all. So to improve this, they're gonna be a circuit that is named as emitter stabilized bias. Okay, meaning that at the bias they add a resistor. Okay, they add a resistor at the emitter they add a resistor. Yeah. Okay, so here we'll have a RC, then you're gonna have R, RB, RC and RE. So they're gonna be 3 resistor for emitter stabilized. For fixed bias, there's only 2 resistor, RB and RC. Okay, so now we want to discuss on what is the emitter stabilized bias. Alright, so emitter stabilized bias is introduced to improve the stability, as I mentioned earlier. Okay, to improve the stability okay, of the fixed bias configuration. Okay, so what they do is by adding a resistor at the emitter junction. Okay, at the emitter junction they added a resistor. So at this point, okay, now let's go to the analysis here. So at this point, okay, you can see, so this is your VB. Okay, this is your VE. Okay, your VB now is equals to, okay, voltage at VB is equals to, okay, voltage at point VB is equals to voltage drop of at the voltage drop at the emitter resistor, okay, IERE, okay, voltage drop at the emitter resistor, IERE, and also plus with the VBE. Okay, so please remember this here. VB, voltage at point base, voltage at base here, point here, is equals to voltage of VBE. Okay, voltage of VBE, which is this area. Okay, voltage at this area plus with voltage of this area must be equals to the voltage of VB. Okay, next if we can go to the VC, so here is your point VC. So VC is equals to VCC, okay, voltage source minus with the voltage drop at resistor RC. Okay, so VCC minus ICRC will equals to the VC. Next is your VE. Okay, so VE will be, alright, so VE here is equals to a voltage of VB. If I can write here, yeah, with common P. Okay, I need to have pencil, yeah. Okay, so remember from our earliest fixed bias configuration, VBE is equals to VB minus VE, right? VBE is equals to VB minus VE. Alright, so how to find this VE? Then we just rearrange this equation. VE is equals to VBE VB minus VBE. Alright, VB minus VBE. Right, so these are the 3 important equations that you need to know. Okay, once you can come up with all of these equations, formula, okay, you understand how formula at all this point can be performed. Okay, it's easier for you to analyze the circuit. Okay, so from here then you can find the value of IE. So current at the emitter is equals to VCC minus VBE. So this is gonna be your BE loop. Okay, VCC minus VBE, okay, over RE plus RB is over beta DC. Okay, so let's look at it, how this IE, IC and IB can be calculated. Okay, so now let's look step to solve. Alright, so step to solve, first of all, same as fixed bias, we need to remove the capacitor. we always have to remove the capacitor. Because of why? Some of you might ask, why we can remove the capacitor? Because in DC analysis, okay, the reactance of a capacitor, okay, will become infinity. All right. In DC analysis, the reactance, okay, the reactance of the capacitor, it will become infinity. So that's why we assume it as an open circuit. This is only applicable or only true for a DC analysis. Okay, it is not true if it is in AC analysis. Okay, so the DC supply VCC then next can be separated into two supplies, which is the BE loop and then the CE loop. So for the BE loop, you need to find the value of IBQ. Some of you might as well ask me, what is this Q mean? So this Q means which is the operating point, meaning that what is the value of the base current for that transistor to operate, meaning that when it is when it is working. So that's why it is mentioned as IBQ, to mention that on this value, it is on this value of current, your transistor is working. Same as well, since that your B is in a Q point, in an operating point, so your collector current also will be in operating point. Okay, so once you so at the BE loop, you can determine the value of base current and also the collector current. Okay, next, once you have determined the BE loop, then only you can go to CE loop. Always remember this sequence. You cannot go to CE loop then only back to BE loop. No, you must always start with the BE loop, then only you can go to the CE loop, because your BE loop is the input. Okay, remember, our base is like a gate. It's the one that controls your transistor. So of course, we need to start with the input. Okay, then only you can proceed to the output. Right? So your output loop is going to be the CE loop. So at the CE loop, then only you can find or determine the VCEQ. Alright, so you cannot determine the VCEQ without determining the value of collector current first. Okay, so now let's go in detail how to make these two loops. Alright, so first step, okay, locate all the capacitors and replace them with an open circuit. So replace here with an open circuit. Alright, next we need to locate the two main loops. Alright, so first of all, yes, we have to locate all these capacitor as an open circuit. So your circuit will be simplified as this circuit. Okay, gonna look as such. So we need to identify the current that is flowing inside this circuit. So you're gonna have the base current here. You're also gonna have the collector current here, and at the emitter you're gonna have the emitter current here. Okay, next, what they said, we need to locate the two main loops. What are the loops? The loop is the BE loop and the CE loop. BE loop is the input loop, CE loop is the output loop. Okay, so always start with the BE loop, then only we can determine the CE loop. Remember the rules. Okay, so now let's look at the BE loop. So the BE loop is at this particular part, yeah, the VCC, RB here, and it goes to the VBE junction, and it goes to the emitter, and it goes to ground. It ends at the ground. It starts with the VCC and then it ends at the ground. Okay, so that is your BE loop. Then what is your CE loop? The CE loop will be start from the VCC again. Okay, the voltage source, it goes to the resistor at the collector junction, at the collector, and then it goes to the VCE. Okay, don't forget we have the VCE here. Okay, VCE. All right, and then it goes to the resistor. Okay, the current will then flow to the emitter part. It will goes to the resistor at the emitter, and it will meet the ground. Okay, so here is the loop that you always need to remember. Okay, I forgot to mention just now, or I did mention but I forgot to write at this area. You're gonna have the VBE. Okay, so at this area you have VCE, so at this area you have VBE. Okay, now let's go to the details of the analysis, right? So now the first one is the BE loop analysis. Okay, always start your calculation by performing the KVL. Okay, please always remember we need to start the calculation by performing the KVL. So what is the KVL? Okay, so the KVL says that our voltage source VCC, okay, VCC is equals to voltage that is dropped across the resistor at the base, okay, which is VBIB, okay, sorry, RBIB, okay. Alright, so this is the value of the voltage drop across this resistor. Next, what voltage that we have? Okay, we also have voltage across the VBE junction. Okay, next, what are other voltage drop that we have? Voltage across resistor at the ammeter. So how to get the voltage here? So it's going to be IE multiplied with the RE, right? So if you write all the equation, you will get the equation to be as such. Okay, your equation will be as such. All right. Next, okay. Next, we need to recall again with the main formula, which from the main formula we know that IE is equals to IB plus IC. This is our main formula, right? And IB is equals to, beta IB is equals to IC. So what we can do here, since that we don't know the value of IC, or IC is not involved in this equation, so we can substitute the value of IC to become beta IB, right, into this equation. So if you substitute this, you will get this equation, right? So we can substitute inside here. Alright, IE is equals to beta plus 1 IB. Okay, beta plus 1 IB. So now, can you define your IB? Yes, right? Because usually the value of beta will be given. You don't have to worry. The value of beta will be given to you. Since that, we can rearrange this equation, and this equation will become as such. And by this, we can determine the value of base current. Okay, once we determine this value of the base current, alright, okay, we know the value of IB, then we can find the value of VB. Where is the value of VB? VB is at this point, right? Let me change the color of the pen so that you can recognize. So where is the VB? Here is the value of VB. Okay, so VB, as mentioned earlier, will be the voltage difference, which is VCC, the voltage source, VCC minus with the voltage drop across the base resistor at the base. Okay, so VCC minus IBRB, then we will get the value of VB. That is one way. Another way is by, okay, if you are able to take from the above part, okay, by knowing the potential difference between the VCC and the voltage difference between here, then you will get the value of VB. Another way is by looking at the down part, which is VB, okay, the voltage here, VB is equals to VBE plus IERE. Okay, it must be plus here, yeah, please, please make correction if your slides written as minus, it's supposedly to become plus here, yeah. So VB will equals to VBE plus VE. So it depends. You can use either one. You can use this equation or you can use this equation. Both are correct. So this is your BE loop analysis, all right, which is your input analysis. Next, look, let's go to the CE loop, which is the output loop analysis. Okay, how the output loop? First of all, we need to perform the KVL. Always start your equation with the calculation with your KVL. Alright, so what are the equations of the KVL? We have a voltage source here, VCC. Okay, based on the KVL, they said voltage source, VCC, must equals to the all voltage that is contained inside the loop, which is IC, RC, plus VCE, plus IE, RE. Right? Okay, so if you rearrange this equation, you will get this. Of course, you will get this. Alright, so now, have you get the IC value? No yet. No, right? Okay, but then the IC, we can assume, if it is a good transistor, we can always assume IE is equals to IC. Or if beta is given to you, if the value of beta is given to you, once you're able to define the value of IB, you can find the value of IC. So there are two ways for you to determine your IC. If they mention that the transistor is a good transistor, then of course you can use this equation, which is IE is equals to IC. But if they mention that they didn't mention anything about good transistor or anything, and they provide to you the value of beta, then you can just use this for you to determine the value of IC. Alright, so now once you got the value of IC, so now let's assume IE is almost equals with the IC. Alright, so we can replace inside this equation, so you will get this equation. Okay, so from here you can get the value of VCE. Okay, you can get the value of VCE. Alright, so you don't have to calculate your value of IE. Alright, yeah, the value of current that you don't have to calculate is the value of IE. Alright, because you can always determine the value of IC based on the value of beta. Okay, sorry, the value of beta will be given to you, usually will be given to you. So we assume that beta multiply with the value of IB, then you will get IC. So in this equation, you have IE, right? Current emitter. Current at the emitter, but we don't know what is the current at the emitter. Okay, either you want to use this equation, IE is equals to beta plus 1 IB, also okay, or if you want to replace that IE is equals to IC, then it's gonna be this equation, also okay. So you can use either this equation, okay, this equation for you to get the value of IE, okay, by replacing inside here, or you want to assume that IE is equals to IC because it is a good transistor. Okay, then you will get then you will find the value of VCE. You are able to find the value of VCE. Alright, and then once you get the value of VCE, then only you can determine the value of VE. Okay, you can determine the value of VE, which is VE is equals to IERE. Okay, IERE. So what is your IE? IE is equals to IC, or IE is equals to beta plus 1 IB. Okay, you can get the value of VE. Right, once you got the value of VE, we know the value of VCE, we can determine the value of VC. Alright, so there are two ways for you to get the value of VC. One is from this equation, another one is by calculate the voltage drop. Same as previous, okay, the voltage drop of here between the VCC and the VC, which is VCC minus IC RC, also okay. Alright, either one you will get similar answer. Okay, okay, if you're clear with this, okay, now let's go to this example number 2. Okay, so example number 2. Okay, now let's look at the example number 2. Okay, example number 2, we need to find the IB, IC, VCE, VB. Okay, what we need to find? We need to find the value of IB. We also need to find the value of IC. Okay, we also need to find the value of VCE. We also need to find the value of VB. There's a lots of value that we need to find. We need to find the value of VC. Next, we need to find the value of VE. Next, we need to find the value of VBC. VBC. Alright, so there are 1, 2, 3, 4, 5, 6, 7. So 7, 1, 2, 3, 4, 5, 6, 7, 7. And we need to assume this silicon is in a transistor silicon. Okay, so always remember what are our first step. First step is we need to remove the capacitor by considering that this capacitor is an open circuit. Okay, so your circuit will then become as such, right? Okay, will look as such, and then here we'll have a resistor and it will goes to ground. Okay, so this is your RB, this is your RC, and this is your RE. Okay, and they said that this is a silicon transistor. Another information that we're gonna have here is your VBE is equals to 0.7, right? Okay, 0.7. Okay, and our VCC is 20 volts. Okay, now once we have simplified version of this, we can go into the what loop? We can go into the VBE loop, right? Okay, now allow me to change the pen color. Okay, let's go to the VBE loop, which is this loop. Okay, okay, so based on the VBE loop, okay, so based on the VBE loop, okay, all right, so what we can do is we can do the KVL, right? So let's say it's very difficult for you. Another way, I didn't mention just now, another way, let's say you are difficult to look the KVL on this, you can always draw another circuit, okay, which will be easier for you. Okay, so this is the circuit gonna be, so here is the ground. Okay, so this is the BE loop. Okay, so I think you are familiar with this. We can do the KVL, right? So the KVL, here is your VCC. Okay, VCC, here is your RB, here is your VBE, here is your RE, right? And if you perform the KVL, it's gonna be, it goes here, right? It goes in, so negative VCC is plus IB RB plus VBE plus IE RE equals to 0, right? Okay, so from here we have some of the values. We have this value, we have this value, we have this value, and we have this value. So we can substitute into the value. So I write up here. Okay, so the first equation is gonna be how much? Negative 20, all right, plus IB, the one that we don't know, all right, and then 430K, okay, plus VBE plus IE 1K equals to 0, right? And then what else? We have the main formula. Okay, remember the beta is given to us, all right? So in this, because in this equation we have two unknowns. What are the unknowns that we don't know? We don't know the value of IB, we don't know the value of IE. So it's difficult to solve if we have only one equation but two unknowns, right? For us to solve these two unknowns, we need to have two equations at least. Okay, so what we can do, we can simplify this into the, by substituting what? By substituting that beta plus 1 IB is equals to IE, right? So these are from the main formula. We substitute inside this. So your equation will be negative 20 plus IB 430K plus VBE plus beta plus 1 IB 1K resistor, right? equals to 0. And from here, we can find the value of IB. Okay, please rearrange the equation. You can find the value of IB. Then you will get how much? 20 minus 0.7. VBE is equals to 0.7 over 430K plus 50 plus 1. Okay, 50 is because of the value of beta is 50, yeah? And then 1K. Then you will get the value of IB. Alright, so you supposedly to get the value of IB is given as 40.1 micro. Please calculate this. Alright, so once we know the value of IB, can we determine our IC? Yes, we can, right? Because beta IB. So beta is 50. Then your IB is 40.1 micro. Then we will get our IC is equals to 2.01 milliampere. Okay, so we have our IB, we have our IC. This is settled and this is settled. Next is we need to solve our VCE. Right, so how to solve the VCE? To solve the VCE, we need to have the output loop. Okay, the CE loop. Sorry, BC loop. Okay, we need to have the, sorry, not BC, CE, right? CE loop, which is the output loop. Okay. So what are the output loop? Okay, so the output loop is this area, right? So this is your output loop. Okay, so now it's quite difficult to, let's say it is quite difficult for you to perform the KVL by just looking at this. Let's redraw the circuit. So how the circuit will gonna looks like? So your circuit will then gonna looks like such, right? Okay, so here is your RE, here is your RC, and then here is your VCC. And all of this is going to the ground. So here is your RE, here is your RC, here is your VCC, and across here we have VCE. Okay, and then how is your KVL? Okay, so now let's say your KVL is on this based on the loop of current, because current is always coming out from the positive. Okay, so what is your KVL equation? It's gonna be, your KVL is gonna be negative VCC plus IC RC plus VCE, okay, plus IE RE equals to 0. Okay, right? Next, we can substitute all this. Okay, we can substitute all this. So your equation will be, where can I write? So I write it here, yeah? Okay, so your equation is gonna be negative 20 plus IC with RC is the 2K, okay, plus VCE, the one that we need to determine, okay, plus IE 1K equals to 0. Okay, and then we have two unknowns, since same as before. Okay, we have two unknown. Okay, IC we know, but with our unknown here is VCE and IE. We cannot have two unknowns with only one equation. So what can we do? We substitute. What can we substitute? The value of IE. We can substitute to what? IE is equals to IC. Okay, so therefore your equation then will become negative 20 plus IC 2K plus VCE plus IC 1K equals to 0. And based from here, you can determine your VCE. Okay, rearrange your equation. You will get your VCE is equals to 13.97. Okay, 13.97 volts. Right, so now you have determined your VCE. Alright, next what we need to determine is the value of VB. Okay, so for the value of VB, I'm using different color of pen. Okay, so for the value of VB, which is this VB, so the VB is equals to alright, VB. Okay, so the value of VB is equals to, okay, VB here. Okay, you can use from above or you want to use from the below, which is the VCC minus IBRB, or we can also, okay, VCC minus IBRB, or okay, VBE plus IE plus VE. VBE plus VE. Alright, so how to find the VE? Okay, VBE is given to you 0.7. How to find the VE? VE is IE multiply with RE. How to find the IE? IE is equals to IC, right? So 0.7 plus IC RE. So we will get our VB is equals to 2.71 volts. Okay, and here we also already have determined the value of VE, which is VE is equals to IE RE, right? So IE RE, which is equals to 2.01, okay, volts. All right, next, what else that we haven't determined? We have settled this. We haven't determined the value of VC. So how to find the value of VC? All right, so VC, which is at this point, right? Here is our VC. So the way to find the VC is by, okay, VCE. We know VCE is equals to VC minus VE, right? VE we have determined earlier, so we can find the VC by VCE plus with the VE, right? So VCE here is 13.97, so plus with the VE, which is 2.01, so we will get here VC is equals to 15.98 volts. Okay, next, what else remain is the VBC. Where is your VBC? VBC is at this particular junction, right? So VBC is equals to, okay, VBC is equals to VB minus VC, right? So VB is the one that we have determined earlier, 2.71, okay, minus with VC. VC is 15.98 volts. So of course we will get negative 13.27. So what is this negative mean? Okay, change the pen color. So what is this negative mean? So this negative mean that this is in a reverse bias. Is this correct? Yes, because of why? VBC is always reverse. For an amplifier, okay, VBC will be in a reverse and VBE will be the forward bias. Okay, so here are the answers. Okay, and here are the solutions in detail. Okay, and I leave exercise number 2 to you guys. All right, so please figure it out. Okay, so this is, you need to determine IBQ, you need to determine ICQ, VCEQ, VC, VB, and VE. So what is this Q mean? This Q means this is the operating point. Okay, you don't have to consider much about this, you just need to add the Q. Okay, meaning that the transistor is working. Okay, that is the working region of the transistor. So please find the value for each of this. Okay, I need you to submit it today, okay, after the class. All right, next let's go to the voltage divider bias. All right, so voltage divider bias is the most widely used. Okay, the one that is very, very famous is the voltage divider bias. Okay, so what are the difference between the emitter stabilized bias circuit just now? Okay, in voltage divider bias we use 2 resistor. Okay, 2 resistor at the base. If you look at the base here, we're gonna have R1 and R2. okay, two resistor. So what is this function of these two resistor? These two resistors as a potential divider network across the supply. Okay, it's gonna be as a potential divider. Okay, so what are the advantages of the voltage divider bias? It provides good Q point stability. Okay, and this method of biasing the transistor greatly reduce the effects if varying beta. So meaning that if the beta, okay, which we know already, beta is equals to IC over IB, right? So if any of this value of current is vary, it will not affect the circuit. It will not affect the whole circuit. It will not affect, what I mean by it is not affect the circuit, it is actually will not affect the Q point lah. Okay, the Q point will remain. So that's why the voltage divider bias has a stable Q point. That's what it is mean by good Q point stability. Okay, it will not be affected although the beta is varying. Okay, alright, so please remember this, it might be asked during the theory. Okay, so only one power supply, we still need one power supply, we only need to have the VCC. Alright, however, we need to apply the voltage divider, in order for our solution here. Okay, so now let's look. If we look at this VB, okay, at the base, so this is our base. At the base now, okay, we have two resistors which is connected parallel, and we have one power supply. Okay, we have one power supply. In this case, for us to find the voltage at this particular area, okay, at this particular junction, we need to apply the Thevenin's law on the voltage divider, which is, okay, so this is going to be voltage R2 over R1 plus R2 multiply with the value of VCC. Always remember this formula. Always remember this formula. This is by hook or by crook, you need to know or you need to apply this. Either you want to remember or you want to understand, it depends. Okay, how to understand? If you want to understand, how to understand is we have one voltage power supply. Okay, and now this voltage power supply is divided parallel to this R1 and R2. Okay, and we need to find another potential between R1 and R2. Hence, because of that, we need to apply a voltage divider rule, okay, which is R2 over R1 plus R2 multiply with the voltage source, which is the VCC. Okay, next is the VC. Alright, so how to find the VC? I think same as previous. Once you understand the previously, then you can find the value of VC, and same with VE. Okay, the only difference is at the VB, point VB, because there is another resistor that is connected parallelly to the base. Okay, the rest is the same. Okay, next let's look what are the configurations here. So to know what is the voltage divider is very easy. There's at the base there are two resistors that is parallelly connected. Okay, one of the resistor will be connected to the power supply, which is VCC, and another resistor will be connected to ground. Okay, so by looking at that, you know already that this is a voltage divider circuit. Okay, so how to solve this? We need to use exact analysis, which is the Thevenin theorem, okay, to find the voltage at point VB, and you can also use an approximate analysis. Okay. Okay, now let's look the most simple step by step how to solve this. Okay, so first of all, of course, when you see the capacitor same as previously, we need to remove them as an open circuit. And second, we need to simplify R1 and R2 by doing a Thevenin theorem. You cannot solve this by R1 and R2 as it is. We need to simplify by using the Thevenin theorem, and then only you can locate the BE loop and the CE loop. Okay, because now at your base it will only have one resistor. Okay, by using the Thevenin theorem, R1 and R2 will become only one resistor, so you can have you can calculate your BE loop. Next, you can proceed with your CE loop. Okay, now let's look how to solve it step by step. Okay, so first of all, we need to remove the capacitor. I think this is all of you guys already got it, right? We remove the capacitor and your circuit will gonna look as such. Okay, next, this is the additional, okay, which we haven't discussed from the previous slide, right? So we need to simplify the circuit by using the Thevenin theorem. We need to simplify by using the Thevenin theorem. How? Okay, we need to simplify the R1 and R2. So your VCC will no longer will become in your simplified circuit. Instead of VCC, it will become V Thevenin. And instead of R1 and R2, it will become R Thevenin. Okay, we want to simplify this to become a simplified version for the base, at the base. So hence, we need to use a Thevenin theorems. Okay, so for the Thevenin theorem, I think most of you guys already know because you guys are electrical students. Okay, we need to apply the R Thevenin. So R Thevenin, how to find the R Thevenin? Because R1 and R2 is parallelly connected, so it's gonna be R1 parallel with the R2, then you will get a new value of R. Next, how about the V Thevenin? The V Thevenin, the value for the voltage, okay, it will become R2 because this is at point VB here, yeah? So it's gonna be across the voltage that will enter the R2, so R2 over R1 plus R2 multiplied with the VCC. So please, by hook or by crook, I need you to remember this at your fingertips. Okay, this is very important, and usually this circuit configuration is the most famous circuit that usually will be asked in your test too. Okay, so now let's look how to further analysis. So once you have simplified your V Thevenin and R Thevenin, we can use the simple rule that we have discussed earlier, the BE loop. Okay, so this will gonna become your BE loop, or the input loop, sorry, yeah, the input loop. So how about the KVL for your input loop? Your KVL is gonna be negative V Thevenin, your new Thevenin, plus IB RTH, right, plus VBE plus IE RE. Okay, so this is gonna be your KVL at the input loop, all right, and the KVL at your output loop. How about the KVL at your output loop? I think it's simple, same as previous. Okay, the KVL at the output loop, let's say it's very hard for you to solve like this, we can always redraw. Okay, don't be lazy, you can always redraw your circuit. Okay, so this is gonna be your VCC, this is gonna be your RE, and this goes to ground. This is your RE, this is your RC, this is your VCC. So it's gonna be like this, the current flow. So your KVL will gonna be negative VCC plus IC RC plus VCE plus IE RE, same as before. Okay, right? Okay, next. Okay, so next, we can proceed with the calculation. Okay, we can proceed with the calculation. So this is the equations of just now, the KVL that I did show to you just now. Okay, so once you got your KVL correct, then you can determine your IB. Okay, so this is same as the emitter stabilized junction, same. All right, next, the CE loop. Okay, the output loop. So this is your KVL. Okay, so the KVL, then you will get same as before. Okay, then you're able to determine the VCE. All right, and now, okay, now, okay, so these are the answers. Okay, let's solve this circuit. All right, first of all, we need to find the R Thevenin, right? So how to find the R Thevenin? Okay, let's say, okay, so of course the capacitor need to be removed. All right, so how the circuit will gonna look like? Okay, so now your circuit, let's draw the complete circuit. Okay, another circuit, so that you can understand well. Okay, so here is your R1. Okay, let's assume this is your R1 and this is your R2. Okay, and this is your R1, and where is your R2? Here is your R2. This is your R1, this is your VCC. Okay, here is your VCC, here is your R2, and then R2 is connected to to ground, so here is your ground. Okay, next, what else? So at this is the point. Okay, this is the point, is connected to the transistors. So here are the transistor, and then we have another resistor here. So this is your RE resistor. This is your RE resistor. This is your RC resistor. Okay. So what we want to do now is we want to simplify this area. Okay, where's my cursor? I need to change the color. Okay, we need to simplify this area so that at this point it will become V Thevenin and R Thevenin. Okay, so how to find the value of R Thevenin? Okay, R Thevenin is very easy, I think, because you guys already know R1 is parallel with R2. Okay, so R1 is parallel with R2, so you will get your R Thevenin is equals to 3.55, yeah, kilo ohm. Please calculate this for me. Okay, R1 is equals to parallel with R2, so you will get 3.55 kilo ohm. How about the V Thevenin? Okay, V Thevenin is the V voltage at this particular point. So to find the voltage at that particular point, it's going to be R2 over R1 plus R2 multiply with the VCC. Okay, so because of that, we can 3.9 kilo over 3.9 kilo plus 39 kilo multiply with the VCC is equals to 22. So you will get here is equals to 2 volts. Alright, hence based on these two value, okay, based on these two value, okay, change color again. Okay, based on these two value, this value and this value, we can redraw the circuit to look as, so here is your V Thevenin. Instead of your VCC, this will become your V Thevenin. Alright, here will become your R Thevenin. Okay, and then it will goes to the base. Okay, here we're gonna become the resistor, and this will connect it to ground. Okay, alright, and across this we have VBE. Don't forget, this is your RE. RE is 1.5 kilo. RTH is equals to 3.55 kilo. VTH is equals to 2 volts. Right, so now can we find at the BE loop? So this is the BE loop. So at the BE loop, can we find the KVL? So here is the current direction. So your KVL will gonna be what? -2, okay, plus IB RTH. So let's write as the value of the RTH that we have determined just now, which is 3.55K, alright, plus VBE plus IE RE 1.5K equals to 0. Alright, so from here we can find the value of VBE is equals to 0.7. Okay, IE, how to find the IE? IE is equals to beta plus 1 IB, right? Okay, so therefore we can substitute, then you can find the value of IB is equals to 2 minus 0.7 over 3.55K plus 140, this is the value of beta, plus 1 okay, multiply with 1.5K. So you will get your IB is equals to 6.05 microampere. Okay, next from here we can go to the CE. So this is the CE. Let's use different color. CE loop. Okay, so the CE loop, let's say you are difficult to get this, to look at this circuit, so don't worry, we can always redraw. Okay, if you're lazy, we can just continue from here. Yeah, so this will gonna be your CE loop. Then you're gonna have, this is your RC, which is your RC is 10K. Then you're gonna still use the VCC. So this is the VCC, we are not using the V-Thevenin, okay? And this is connected to the ground. And your I is gonna be on that way. So your KVL will be how? So the KVL will be negative 22, alright, plus IC 10K, okay, plus VCE Q, alright, don't forget about that. Oh, I forgot to write the Q, yeah? Don't forget to write about the Q. Okay, right, next, what else? VCEQ plus IE RE. RE is 1.5K equals to 0. Alright, so from here we can find IE is equals to IC. Right, so what is the value of IC? IC we can get, which is beta IB that we have determined earlier. So what is the beta? Beta is 140, IB is 6.05 micro. So we will get IC is equals to 0.846 milliampere. Alright, so we can substitute inside the equation of the KVL just now. So we can get our VCEQ is equals to 12.271 volts. Okay, right, so this is not finished yet because the questions ask about the VC and all others value, right? So from here we can find the value of VE. What is the value of VE? VE is easy, IE multiply with RE. So what is the value of IE? IE, either you want to use IB beta plus 1 RE 1.5K, or you want to use IC RE, both are acceptable. Okay, don't worry, it might be sometimes slightly difference in decimal, but it is acceptable. Okay, so it's gonna be 1.279 volts. Okay, if you are using IERE, then you will get 1.279 volts. So from here we can find the value of VC, which is VCEQ plus VE, right? So it will be 12.271 plus 1.279, then you will get the value is 13.55 volts. Alright, and from here we also can find the value of VBC, which is VB minus VC. Okay, how about the VB? Okay, we didn't determine the VB yet. Okay, now let's determine the VB first. Okay, so we know VBE is equals to VB minus VE, and hence VB is equals to VBE plus VE, right? So 0.7 plus VE that we have calculated earlier, 1.279, then you will get 1.979 volts. Okay, this is your VB. Okay, so your VBC VC will be 1.979 minus VC 13.55. Then you will get your VBC is in negative form, 11.571 volts. So this is true because our VBC is always in reverse bias. Okay, so I think we have determined, okay, we have determined 1, 2, what else, 3, and then 3, 4, 5, 6, 7, 8, 9. Okay, so we have determined 9, and this is the solution. Okay, if you want to look at the solution, all right, I share the solution here, and I leave this exercise 3 for you to try. Okay, so there are 2 exercises that you need to submit, exercise 2 and exercise 3. Okay, so please submit this as your attendance. Right, thank you so much and see you next time.